Hello, my name is Domenico Quagliarella, and I work at CIRA. My job is aerodynamic calculation and design. In this video, we start the educational journey introduced in the previous lesson. What do a windy bridge, a skyscraper, a surfer, and an airplane have in common? In the first two cases, the fluid is moving around the objects. In the first and fourth case, the objects are moving into it. But what happens between solids and fluids? During the interaction between them, a force rises. It's called drag. Let's try to understand the effect of this force. On the skyscraper, the wind generates a huge load of thousands of tons. On the other hand, for objects moving in the fluid, such as an airplane, the effect of the drag is that of slowing down their motion. Energy loss occurs during this process. For this reason, in order to keep an object moving in the fluid, you need to overcome the drag with a thrust. For the skyscraper, you need to evaluate the loads reliably in order to design their structures strong enough. It is very important to compute exactly the drag of the object in the fluid. It is possible to reduce the drag. Probably everybody of you has experienced riding a motorbike that if you want to gain speed or cut down on fuel consumption, you need to lean forward. What can you learn from this experience? If you lean forward, you reduce your cross-sectional area. This is always the first principle to apply for drag reduction. Then, in order to have a better result at the same cross-sectional area, you need to have a more aerodynamic shape. This is the second and most important principle for drag reduction. What happens when solids of different shapes are moving in the fluid? Look at this animation. Let's try to understand what's the difference between a sphere and an aerodynamic body having the same cross-sectional area when they are in airflow at a speed of about 350 kilometers per hour. Also, if the cross-sectional area is the same, the aerodynamic body drag is 10 times less than the drag of the sphere. The same effect can be noticed on a motorbike. When you lean forward, you're improving your aerodynamic performance. In fact, not only you're reducing your cross-sectional area, but you are also getting close to a more aerodynamic shape. This is why skiers or bikers' helmets, disc wheels, and racers have got their eccentric shapes.
Nelle auto o nelle moto da competizione.
What is a fluid? All the matter which is in a gaseous or liquid state is called fluid. A fluid is made of billions of molecules separated by blanks. If you watch on a bigger scale, let's say bigger dimensions compared to the molecules' distances, the fluid seems to be uniform and continuous. This allows to study the behavior of a real fluid, not through the study of motion or every molecule, but by replacing it with a physical model of fluid, which can be considered continuous. This model is able to approximately describe the statistical average behavior of a real fluid. Let's now evaluate the main physical quantities of this model of fluid. We use an elementary volume of fluid that is extremely small, but it still contains billions of molecules. By using this model, the density of the fluid will be the molecular mass divided by the elementary volume which contains them. The speed of the fluid in a point will be the average speed of the molecules contained in the elementary volume. The elementary volumes of fluid, that we call particles of fluid, obey the Newton's second law of motion. The acceleration of the volume depends directly upon the net force acting on it. Let's examine what forces are acting on it. In this animation, you can easily see all the forces acting with a direct contact on the surface of the volume. The forces perpendicular to the surface are the pressure forces. The forces tangential to the surface depend on the viscous friction. Pressure and viscous friction are not the only ones acting upon the volume. We also have the weight. Let's try an experiment. Let's pour some water and some oil on a surface and notice how these two fluids behave in two different ways. Water flows rapidly while oil takes much more time to cover the same distance. This happens because water is not a very viscous fluid. On the contrary, oil is a very viscous fluid one. What's the viscosity of a fluid? Fluids tend to deform under the action of tangential forces. The ratio of the tangential force and the speed of this deformation is a measure of the behavior of different fluids, such as water and oil. This ratio is called viscosity. We notice that the fluid particles slow down, getting closer and closer to the surface of the object. On the surface, they are motionless. This last condition is called no-slip condition. This aspect of the viscous friction is very important to understand the drag generation. It is always true, no matter what type of material the surface of the object is made of. Only the surface roughness has a direct effect on the drag and not the material. Looking back at the experiment, the different behavior of water and oil is due to their different viscosity.
E dell'olio dovuta alla differente viscosità.
Being known the forces acting on the elementary volume of fluid, they can be introduced in the Newton's law to be related with the acceleration of the mass of the fluid. In this way, we obtain an equilibrium equation. The vectorial sum of pressure forces, viscous forces, and inertia force, E dest, the mass of the fluid particles multiplied by its acceleration, must be zero. This acceleration determines instant by instant the motion and the trajectory of the particle. Let's now recall two fundamental concepts before going on with the explanation. 1. Weight is not accounted for in the forces because it's balanced by Archimedes' thrust. 2. The viscous friction converts part of the fluid kinetic energy into heat. This phenomenon is accounted for in the energy conservation equation. In the case explained before, the sphere and the aerodynamic body move very fast into the air, which has a low viscosity. In these circumstances, the effect of the viscosity are significant only at the borderline zone between fluid and solid that is called boundary layer. We already know that the particles can't flow on the surface of the solid, but they can freely flow around it. Therefore, in the immediate vicinity of the surface, the flow must stop no matter what level of viscosity the fluid has. Viscosity has a direct influence on the thickness of the boundary layer.
Quello di ampliare o restringere lo spessore della zona in cui avviene il rallentamento del fluido.
Thus, the least the viscosity is, the thinnest the boundary layer will be.
Minore sarà lo spessore dello strato liquido.
Anyway, it's important to observe that even a very low viscosity will produce a considerable drag. Only a fluid with zero viscosity will flow around the body without producing any drag. A fluid with zero viscosity is called ideal fluid. In this case, the no-slip condition is not true anymore. Just for example, the liquid helium at extremely low temperatures behaves like an ideal fluid. Have you ever wondered why when you ride a motorbike your hair is blown chaotically and your jacket seems to be sucked? Well, let's try to answer to these questions. Let's watch in detail what happens to a body moving in a fluid. Only the particles of fluid in the immediate vicinity of the surface are acting on it by applying some forces. On each point of the surface, the adjacent particle of fluid generally applies a perpendicular force, the pressure, and the tangential one, the friction. In order to evaluate the drag, the algebraic sum of all components of pressure and viscous forces along the direction of body motion has to be considered. The friction forces always have the effect of opposing the motion of the object. Pressure forces behaves differently. In fact, it always acts perpendicularly to the surface. In proximity of the front part, also called leading edge, the pressure forces has a component oriented in the direction of the drag. At the maximum thickness, this component is zero. In proximity of the trailing edge of the body, it is oriented in the drag's opposite direction. Thus, from leading edge to the maximum thickness point, the effect of the pressure is of opposing to the motion. Then, from the maximum thickness point to the trailing edge, the effect of the pressure is of helping the motion. The algebraic sum of all these components is the portion of drag due to the pressure. It is now easy to deduce that depending on the shape of the object and on the flow condition, the part of the drag due to pressure can lower or greater than the drag due to friction. It can be mathematically demonstrated that with no viscosity, that is, with an ideal fluid, the sum of the components of drag due to pressure are zero. This is with an ideal fluid. The drag due to pressure is zero. In order to understand the genesis of the drag due to pressure in the case of a viscous fluid, we have to consider the ratio between the speed of the fluid and the pressure. For an ideal fluid, the pressure is directly related to the speed of the fluid according to Bernoulli's law. As the speed of the fluid increases, the pressure decreases, and vice versa, as you can see on the figure. Therefore, a decreasing pressure creates an accelerating force on the fluid particle. On the other hand, an increasing pressure creates a braking force on the fluid particle. For an ideal fluid, there will be two stop points, at the leading and at the trailing edge of the aerodynamic body. For an ideal fluid, this phenomenon produces no drag. For a real fluid, on the contrary, the effect of the viscosity must be added to the effect of the pressure. From the leading edge to the maximum thickness point, the particle will be subjected to the accelerating effect of the decreasing pressure and to the braking effect of the friction. Therefore, it will reach the point of minimum pressure with a momentum lower than that of zero friction condition. In addition, from the point of the minimum pressure on, both the increasing pressure and the friction will tend to stop it. The result is that the particle of fluid may stop before reaching the trailing edge. This phenomenon is called stall. In this condition, a large rotating flow creates behind the stall point, and the main flow moves around it. The pressure in the wake region is much lower than that in the same region, but without the wake. This causes the drag due to pressure to be much higher than that due to the friction. Luckily, the stall happens only for stocky bodies, for which the pressure jump is sudden. For thin bodies, on the contrary, where the pressure variation is much slower and gradual, the external flow through the viscosity trails the boundary layer. This fact avoids that the stall occurs. In these conditions, the turbulent wake does not create, and the pressure due to drag and the portion drag due to pressure is negligible. Well, now you're able to explain what are the effects of the air on the motorbike and on your body. We are now at the end of the lesson. We have seen the drag produced by the viscosity of the fluid with no lift. But we have to remember that the drag of a body in a fluid can also be caused by other phenomena. For example, a ship sailing the sea produces superficial waves that move and waste energy. An aircraft in supersonic regime creates very strong pressure waves, called shock waves, that move and waste energy in the air. Finally, a wing that creates lift produces two vortexes at its tips, sometimes visible with special weather conditions. The vortex also wastes kinetic energy in the air. I thank you for your attention. Goodbye, and see you next time.